Have you ever stopped to think about something like table salt? I mean, why does it have a melting point of over 800 degrees Celsius? It's because it's not just a random pile of atoms. It's this perfect, ordered crystal, and it's held together by an absolutely immense energetic force. Today, we are diving deep into that force, lattice energy. And that's exactly the question we're going to tackle. In this explainer, we're going to unpack the whole concept of lattice energy, what it is, how we can calculate it, and what key factors make it so incredibly powerful. So here's our game plan. We'll start with the basic definition, then we'll look at all the forces at play inside a crystal. From there, we'll get into the math with the Born-Lande equation. After that, we'll see how we can actually use this theory to compare real compounds, and finally, we'll talk about where our model has its limits. All right, let's jump in. Okay, first things first, what is lattice energy? Well, probably the best way to wrap your head around it is to imagine building an ionic crystal, piece by piece, right from its most basic components. So, picture this. You've got a huge cloud of positively charged cations and negatively charged anions. They're all in the gas phase, just kind of floating around, infinitely far apart from one another. Since they're not interacting at all, we just define the potential energy of this whole system as zero. It's our starting point. Okay, now let's bring them all together. As these ions get closer, their opposite charges pull them in, and they start snapping into place in this highly ordered, repeating 3D pattern. That's our crystal lattice. As this happens, the potential energy of the whole system just plummets. This process releases a massive amount of energy, and what you're left with is an incredibly stable solid. And that massive energy release, that's what we call lattice energy. So to be really precise about it, here's the formal definition. It's the energy change that occurs when 1 mole of gaseous ions come together from infinite separation to form 1 mole of a solid ionic crystal. The textbook example is, of course, making sodium chloride. You take gaseous sodium ions and gaseous chloride ions, and they combine to form the solid salt crystal. Now, because energy is always released when this stable lattice forms, the process is always exothermic. And that means the value for lattice energy is always negative. For sodium chloride, it's a pretty hefty minus 787 kilojoules per mole. But here's the thing. A crystal isn't just about simple attraction. It's actually a really delicate, intricate balance of competing forces. So yeah, the main event is definitely the powerful attraction between the positive cations and the negative anions. That's what holds the whole thing together. But at the same time, you got all the like charges pushing each other away. Cations repelling other cations, and anions repelling other anions. And on top of that, if you try to squish the ions too close together, their electron clouds start to overlap, and that creates a really strong short-range repulsion. The final, stable crystal structure is the one geometric arrangement that perfectly maximizes all the attraction while minimizing all that repulsion. So, how do we actually put a number to all this? How can we calculate the total energy of this complex dance of attraction and repulsion? Well, for that, we need a really powerful theoretical model. At its heart, the idea is actually pretty simple. The total potential energy of the lattice, its lattice energy, is really just the sum of all the attractive forces pulling it together and all the repulsive forces pushing it apart. And this equation, the Born-Lande equation, captures that balance perfectly. This first big chunk here, the negative term, that's all about the net electrostatic attraction. Then you have this second term, the positive one, which accounts for that short-range repulsion when electron clouds get too close. It's literally attraction versus repulsion in a single formula. Now, I know that equation looks a little intimidating, but every single variable in there tells us something really important about what makes a lattice strong or weak. So let's break it down. Let's start with something really cool, the Madelung constant, which is that A value. This isn't just some random constant. It's a purely geometric factor that basically adds up every single attraction and repulsion an ion feels from every other ion in the entire crystal. And its value is totally unique to the crystal's specific structure, whether it's the shape of table salt or something else entirely. Then we have the Born exponent, N, which handles the repulsion term. You can think of it as a measure of how squishy the ions are. And as you can see here, ions with bigger, puffier electron clouds, like the ones with a xenon configuration, have higher N values. That just means they resist being compressed more. To get the N for a whole compound, you just take the average of the values for its cation and anion. But listen, if you just want to make quick, accurate predictions, you really only need to focus on two things. First and foremost, the product of the ionic charges. This is by far the biggest factor. Because lattice energy is directly related to these charges, doubling them makes a massive, massive difference. Second is the distance between the ions, R. Since it's in the denominator, smaller ions that can pack closer together will have a stronger attraction and therefore a greater lattice energy.
All right, that's enough of the theory. Let's actually put these principles to work and compare some real ionic compounds.
So let's start with our good friend sodium chloride. We've got a +1 cation and a -1 anion. Pretty simple. The product of those charge magnitudes is just 1. Now let's switch to magnesium oxide. In this case, we've got a +2 cation and a -2 anion, so the product of the charge magnitudes is 4.
And this right here shows you why charge is king. The charge product for magnesium oxide is 4 times bigger than for sodium chloride. But look at the lattice energy. It's almost 5 times greater. Sure, the ions are slightly different sizes, but that's a tiny effect. The gigantic difference in stability comes almost entirely from those bigger ionic charges.
So here's your cheat sheet. If you ever need to rank compounds by lattice energy, this is the way to do it. Step 1 always is to figure out the product of the charges. Then you group the compounds by that product. A +2/-2 group will always have a much higher lattice energy than a +1/-1 group. Only after you've sorted them by charge do you look at size. Within each group, the compound with the smallest ions, the one with the shortest distance between them, will have the greatest lattice energy.
Now, the Born-Lande equation is an amazing tool. It's incredibly useful. But like any good scientific model, it's built on a few key assumptions. It's a bit of an idealization of reality. The biggest assumption here is that we're treating ions as if they're perfect little billiard balls, hard, spherical, and not at all deformable. The model also assumes that the bond is 100% ionic, meaning the electrons are completely transferred and the only force at play is electrostatics. Of course, in the real world, no bond is perfectly ionic. There's almost always a little bit of electron sharing going on. But here's the really incredible part. For simple compounds like sodium chloride, where those assumptions are pretty close to being true, the value you calculate with the Born-Lande equation is remarkably close to the actual experimental value. I mean, look at that, -778 versus the real value. That's fantastic agreement. It tells us that this model, even with its simplifications, does a brilliant job of capturing the fundamental physics of ionic bonding.
And that leaves us with one final thought to chew on. This whole framework is built on the idea of perfect hard spheres. But what happens when that assumption starts to break down? What happens when a small, highly charged cation starts to tug on the big, fluffy electron cloud of an anion and distorts it? Well, that's when you enter the much more complex and fascinating world of polarization and covalent character. But that, my friends, is a story for another time.